Okay, friend, we start today's lecture. I am going to share the screen. Friends, is the screen is visible? Please give me response. That is screen is visible.
Yes, sir.
Okay, Rutuja, thank you. Okay, in last lecture we are came to this derivation. At the end of this derivation, and we in last lecture we studied in detail this derivation. Just I am taking the flashback of this derivation. If we choose the two coordinate, that is new coordinate, q1 is equal to x1 plus x2 and q2 is equal to x1 plus x2. Just differentiate these two coordinate, that is a q1 is equal to x1 plus x2, that is the addition of displacement, and q2 is the subtraction of the displacement. And if you take these two additional coordinate, then d2 q1 by dt square is equal to minus omega 0 square q1, and d2 q2 that is the subtraction of the displacement, d2 q2 by dt square is equal to minus omega 0 square plus 2 omega square and bracket into q2. From above two equation, that is the equation number 2.5 and 2.6, we represent the simple harmonic motion with the frequency. That is, there we are going to get, we are going to see the simple harmonic motion SHM with frequencies. And we know that there is the SHM for two frequencies which are that is omega 1 is equal to omega 0, that will be equal to root of g by L. G is, we know that, acceleration due to gravity, and L is the length of the pendula, that is the L. Then what about the omega 1? That is omega 1 is equal to omega 0. Omega 0 is equal to root of g by L. And what about the omega 2? Omega 2 is equal to omega 0 square plus 2 root of omega 0 square plus 2 omega square. That is this equation. That is these two equation can give these two equation, that is omega 1 and omega 2, gives the value of the two frequencies. That is the value of two frequencies, and these are the two frequencies in SHM with frequency, where omega 2 is also k by m. That is, k is, we know that it is the constant of the spring constant, and m is the mass of the bob. Then thus coupled pendula Thus, coupled pendula oscillates simple harmonically with two frequencies omega 1 and omega 2, or rather than omega, it will be indicated by omega 0 also. Then that is the coupled up simple pendula, or the coupled simple system of the two pendula A and B with the two frequencies omega 1 and omega 2, and which are known as the normal mode, in which all the particle of the oscillating body undergoes the same displacement from mean position at a given time. Here we know that these two frequencies are known as a normal mode, and in which all the particles of the oscillating body, it may be in the same direction or in opposite direction or in one same direction, that will be known as an, all the particle of the oscillating body undergoes the same displacement from mean position at a given time. That is, it will be at the same displacement at a same time, or this same instant of the time. Whatever may be the complicated motion of the coupled oscillation pendula can be described in terms of the normal mode using coordinate q1 and q2 are called as the normal coordinate, where we know that where the simple harmonic motion is to be complicated, is to be complex, then the coordinate q1 and q2, these two coordinate are known as a normal coordinate. That is the normal mode and normal coordinate we have to study, and hence in next point or next topic we are going to study the normal mode and normal coordinates. That is the 2.3 topic number 2.3, and it is the normal mode and normal coordinates. That is, what is the normal mode and what is the normal coordinate is to be studied in this topic. When coupled system, that is when coupled system is the couple, when a coupled system oscillate a single mode, then oscillating part then same frequency, oscillating parts have same frequency and same phase constant, that will be seen already. In given mode, the relative displacement is governed by the characteristic constant or the ratio of the amplitude. Just here we are going to calculate the ratio of the amplitude of the two oscillatory system in coupled oscillation, and that will be seen already. The solution of the differential equation 2.5 and 2.6 are expressed either in the form of the sine and cosine of the trigonometric function. Here, if we are going to calculate the differential equation that will be shown above, that will be 2.5 and 2.6, and we have to consider the cosine and sine and cosine function of the two. If consider the q1 is equal to, consider this, that is q1 is equal to a1 into cos of omega 1 t. You know that the q1 is the normal coordinate, a1 is the amplitude, and cos of omega 1 is the frequency, and t is the time instant. Okay, here q2 also, what about the q2 a2 is the amplitude for the second pendulum, and cos of omega 2 is the also amplitude for the second pendulum, but instant of the time is the same, that will be the t, that will be the small t. Then therefore in terms of the original coordinate q1, original coordinate x1 and x2, there is the displacement. Solution become x1 is equal to 1 half of q1 plus q2. That is the addition of the two normal mode. And if addition, if put the value of the q1 and value of the q2, then we get the 1 half a1 cos of omega 1 t. That is a1. That is 1 half cos of omega 1